This video is now going to look at hyperbolic differentiation. We can differentiate both the hyperbolic functions and their inverses. So starting off with our sine, cosh and tanh, you will see the results quoted here, which look very similar to the type of differentiation that you have undertaken when doing trig differentiation. One exception is that cosh of x differentiates to sine of x with no minus sign. Let's have a look at why that is. If we take cosh and replace it with its exponential definition, we can then differentiate those exponential functions. So bringing the half in front, we then have e to the x differentiating to e to the x, and e to the minus x differentiating to minus e to the minus x. That we now recognise as the definition of hyperbolic sine, and therefore we have derived the result for the differentiation of hyperbolic cos. Now let's have a look at the other questions on page 43. We're being asked to differentiate e to the x multiplied by sine of 2x. Therefore, we are being asked to differentiate a product, and we apply the product rule, leaving e to the x alone, differentiating hyperbolic sine, differentiating e to the x, and leaving sine of 2x alone. We then factorise by taking e to the x out. Question 2, we're being asked to show that the second derivative of a cosh 2x minus b sine 2x is 4y. So taking y, we differentiate using the chain rule in each case and the results above. We then repeat the differentiation to obtain the second derivative, again using the chain rule, and then we factorise, and you can see that having taken a 4 out, the expression that's left in the bracket is in fact y, so therefore we have shown the second derivative is 4y. We're now going to move on to question 3, which comes from the textbook but is a useful question to work through. Part A derives the result for the differentiation of the inverse of hyperbolic sine, and we could do a similar piece of work for hyperbolic cos or hyperbolic tan and their inverses. We're then asked to go on to produce the series expansion. Now, as we haven't got a nice set of series expansion already completed for hyperbolics, we'll be using Maclaurin's here. So the question will help us revise our Maclaurin's series. Now, part A. I'm going to let y equal inverse of hyperbolic x, and that means that x equals sine of y. I then differentiate with respect to y, so we get dy by dx, sorry, dx by dy equals cosh of y. And I'm then going to use my identity, my hyperbolic identity that I've got here and rearranged for cosh of y, so that I can write dx by dy in terms of sine squared y plus 1. That then allows the hyperbolic to be replaced with x. And finally, I reciprocal dx by dy to get dy by dx, and therefore obtain the required result. So that's how to derive the inverse hyperbolic differentiation result. Now let's have a look at B, where we are using Maclaren's. We're going to let f of x be arc sine of x, and we need to know its value when x is 0. We'll then differentiate this result, which is our result that we obtained in A. If we sub 0 in, we will get a value of 1. So that's our first non-zero term. I've then written the first derivative with a negative index so that I can use the chain rule to obtain the second derivative. So I'll bring the minus a half in front and reduce my power by 1, leaving the contents of the bracket in the bracket, and I multiply by the differential of the bracket. And that results in this expression here. If I sub 0 in, I get a value of 0. So as I've been asked to find the first two non-zero terms, I need to differentiate one more time and hope that the next one gives me a non-zero term. So the third derivative, this expression here, I'm going to need to differentiate using the quotient rule. So we are going to need x squared plus 1 to 3 over 2, and that's going to be squared. Bring the bracket x squared plus 1 to 3 over 2 onto the top. Multiply it by the differential of the function on the top, so that's going to be multiplied by minus 1. We're then going to take away the minus x, which means we're going to get a plus x, and we're going to multiply it by the differential of the bottom. So that's going to be 3 over 2 times by bracket, which is going to be x squared plus 1 to the half, which we're reducing power by 1, and we need to multiply by the differential of the bracket, so we need a 2x. So that simplifies to, bring this up over here, f3 x simplifies to x squared plus 1 to 3 over 2, and that's a minus there. And then we have 3x squared to the x squared plus 1 to the half, all over x squared plus 1 cubed. Now, with a few more lines of algebra, this will all simplify down to 2x squared minus 1 over x squared plus 1 to the 5 over 2. And if I sub 0 into that, I get minus 1. So I found the two non-zero terms. So that means that arc sine of x can be approximated by using Maclaren's x minus x cubed over 3 factorial, or x minus x cubed over 6. I appreciate that there may be some more working here, which may be needed. Okay, now what we've got here is they've given us the general term for the expansion. Okay, so we're now going to use that to help us with part C, and then part D, and then we'll finish off with part D. So for part C, we use the general term we're being asked to come up with x to the power of 5. So that means that 5 is going to equal the 2n plus 1. So 5 equals 2n plus 1. And that means that n will be 2. So the coefficient is going to be, using the expression in the question, minus 1 squared 2 times 2 factorial over 2 to the 4 factorial squared. And we're also going to have the 2n plus 1 that's on the bottom of the x to the 5, so that's going to be a 1/5. So that gives me a value of 3 over 40. So that is the coefficient of the x to the 5 term. So now I can do part D. I'm being asked to use my approximation up to the x to the 5th term to find the value when we sub in 0.5. So inverse of hyperbolic sine of 0.5 is going to be approximately x, that's 0.5, minus 0.5 cubed over 6 plus the 3 over 40 that I worked out in part C. Times by the 0.5, and it will be to the power of 5. So if we put all that in our calculator, we get an approximation of 0.48151. And then last but not least, part E, the percentage error for the approximation. Part E, we will have our approximation minus the actual 0.5 divided by the actual. That gives us a percentage of 0.062%. So that question has shown us how to derive the result for the differentiation of an inverse hyperbolic trig function, and then has asked us to use it in the context of a Maclaren's expansion, including the use of the general term. So that's hyperbolic differentiation.